Now in this video I'm going to go through some of the calculations and note that some of the calculations that I'll present here for ANOVA I already performed. So when we take a look at the ANOVA steps, the first step mathematically is to calculate the sum of squares using the equations in the previous video. So I'm just going to go ahead and present those data as I've calculated. So from the data, the raw data that were used in the equations, the sum of squares between was found to be 50.82. The within value was 47.37, and sum of squares total is 98.19. These can be calculated manually or with any software program designed to carry out these calculations. In calculating the degrees of freedom, these are a little bit more straightforward, and these are prescribed equations for the one-factor ANOVA, and note this is not repeated measures. The degrees of freedom between is the number of groups in your design. In this case, we had 5 groups. Subtract 1. So our degrees of freedom for the between term is 5 minus 1, which is 4. The within term is the difference between the total number of cases in our study. That is our entire sample size indicated by an uppercase N. Subtract the number of groups. So recall that we had 7 businesses per group times 5 groups. That gives us a total sample size of 35 minus the 5 groups gives us 30. And our degrees of freedom total is just our sample size. Subtract 1, which is 35 minus 1, and that's a 34. Now moving on to step 3, we then use those data from slide 14 to calculate the different variance terms, or the specific term used to indicate the variance in ANOVA is the mean square. So mean square and variance are terms that are used interchangeably, hence the acronym here, analysis of variance. And that's what we're doing here in this type of approach, is we're analyzing variances in order to answer our research question if there's a systematic statistical difference between the 5 groups. So our mean square between and our mean square within are calculated as the ratio of the sum of squares between divided by the degrees of freedom between to get the variance between, or the mean square between, and likewise we match up the within terms where we divide the sum of squares by the degrees of freedom for the within term. Now I'm just going to substitute the data from slide 14 where I have 50.82 divided by 4. That gives me a variance between of 12.71. The within variance term, or mean square term, is simply the 47.77 divided by 30, and that gives us a much smaller variance term when we take a look at the data, the variability inside all the groups simultaneously. Compare the numbers at 1.59 as compared to the variance between the averages of the 5 groups. Much bigger sense of variability between the groups than we see within the groups, and that indicates to us that there is very likely some type of systematic pattern indicating that there are clear deviations between the groups. And to confirm that, we calculate the F statistic, or sometimes referred to as the obtained. And the obtained statistic is just simply the ratio of these two variances. So if the variance between the groups far exceeds the variability inside the groups, then that will give us a relatively large F obtained. So we substitute the values here for mean square between and mean square within. This is just the prescribed way of carrying out these calculations, and we end up with an F obtained of 7.99. Now, what do we do with this number? We compare this number to our critical value. And recall in the earlier video on slide 13, we looked up the critical value based upon the design of the study and the sample size and the type 1 error rate to be 2.69. So based on the actual data, we see that the F value of just about 8 is far exceeds the critical value. So before we get into the final interpretation here, we asked the question was what is the effect of the total number of participants or cases on the F ratio? That would be the F obtained. Now recall that the degrees of freedom for the within term is the sample size minus the number of groups. So if we have a fairly large sample size relative to the number of groups, then we're going to have a big degrees of freedom for the within term. If n is much larger than k, and if you recall, our n is 35 and our k was 5, so that's a fair size difference. Now if that gives us a large degree of freedom within term, then the mean square, the variance within, will be a small value because the degrees of freedom within is in the denominator of the mean square equation. Now that will give us a small mean square within. Now if the mean square within is small, then the calculated F ratio will be large because the mean square within is in the denominator of the F obtained value. And so going back to step number 1 here, just to recall that our mean square within, which is in the denominator of our F obtained, is going to be a relatively small value because the degrees of freedom is a large value, and it's large because of the big difference in this between the sample size and the number of groups. So when we follow these 3 steps through and connect number 1 to number 3, the general pattern here is that as the sample size increases, the statistical power will increase. In other words, the ability to find a statistically significant difference between the groups is much more likely, if it truly exists, when we have a large sample size. So this ends this part of our coverage of analysis